Have you ever really, truly stopped to wonder why the floor beneath your feet is, well, solid? Why you don't just sort of sink through it? You know, the answer isn't just about atoms being tiny hard balls. It's much deeper. It's a fundamental quantum rule, an invisible architecture that literally shapes everything, from the chair you're sitting in to the most distant stars in the sky. And today, we are going to pull back the curtain on that very rule.
Welcome to our Quantum Deep Dive, where we get into the nitty-gritty of the rules that build reality itself.
And our guide for this incredible journey is the fantastic essay on Fermi-Dirac statistics. That's right, it's by Georg Oeschnepat, and we're going to break down his core ideas to show you why this isn't just some abstract physics. Nope. This is the operating system for our entire universe.
So, here's how we're going to do it. First, we'll start with a fundamental puzzle that had physicists scratching their heads for years. Then we'll reveal the incredibly simple rule that just solves it all, and see how that one rule builds everything from atoms to stars. Exactly. Then we'll see how it powers all of our modern technology. And finally, we'll look ahead to what this all means for the next quantum frontier.
All right, so let's dive right into that puzzle, the basic mystery of why the world as we know it can even exist in the first place. I mean, seriously, just think about it for a second. We're taught that atoms are mostly empty space, right? So why is stuff solid? Why doesn't the immense gravitational pressure at the core of a star just instantly crush it into nothing? These are the kinds of questions that classical physics, the physics of Newton and Maxwell, it just had no answer for.
Right. The old school way of thinking, which is called Maxwell-Boltzmann statistics, it treated particles like tiny individual billiard balls that you could track and predict. But here's the thing. Down at the quantum level, particles are more like indistinguishable fuzzy clouds of probability. And when you try to apply those old billiard ball rules to these quantum clouds, the math just completely falls apart. It predicts a universe that looks nothing like the one we actually live in.
So the old rulebook was totally useless. The solution had to come from a completely new way of thinking, a revolutionary new rule that governs the actual building blocks of matter.
And the main characters in this entire story are particles called fermions. Now, these are the guys that make up all the stuff we see and touch. Electrons, protons, quarks, you name it. They are the fundamental bricks of our universe. And they all share this one defining characteristic, a quantum property called spin, specifically a half-integer spin, and that little detail dictates everything about how they behave.
And because of that unique spin, they all have to obey this shockingly simple yet incredibly profound cosmic law. It was formulated by Wolfgang Pauli back in 1925, and we call it the Pauli exclusion principle. All it says is this: two identical fermions can never, ever, ever, ever be in the same quantum state at the same time. You can think of it as the ultimate rule of personal space for particles. No exceptions.
And this is a perfect way to picture it, as two fundamental tribes of particles. On one side, you have our fermions. They're the antisocial individualists of the quantum world. They absolutely demand their own unique quantum state. And it's this refusal to pile on top of each other that gives matter its structure and its solidity. And on the other side, you've got the bosons, like photons, the particles of light. They're the complete opposite. They are the socialites. They love to crowd into the same state, which is exactly why you can have things like incredibly powerful coherent laser beams.
So, one simple rule: no two fermions in the same state. That sounds kind of small, right? But its consequences are, well, they're anything but. This single principle is basically the master architect of the entire cosmos. Let's see how.
Okay, picture an atom. As you add electrons, which remember are fermions, they can't all just pile into the coziest, lowest energy level. The exclusion principle acts like a bouncer at a club, saying, nope, sorry, this space is taken. So the first two electrons fill up that first shell. The next ones, they're forced to go to a higher energy shell, and then the next ones go to an even higher one, and so on. This forced stacking is literally what creates the electron shells you learned about in chemistry. It's the reason we have a periodic table with all its amazing, diverse elements. Without this rule, pretty much every element would just behave like hydrogen.
So, and this is the crucial part, this quantum-level standoffishness creates a real, tangible outward force. It's not pressure from heat or anything like that. It's a purely quantum mechanical effect called degeneracy pressure. It's the universe's way of saying, hey, back off. You can't squeeze these fermions any closer together.
And this brings us to a truly epic cosmic showdown. We've seen this rule build tiny atoms, so now let's scale things way up.
What happens when you pit this subtle quantum pressure against the most relentless, crushing force in the entire universe? Gravity.
And this number right here gives you the incredible answer. Inside a dying star, a white dwarf, gravity is trying with all its might to crush everything down to a single point. But the electrons, being stubborn fermions, they push back with degeneracy pressure. And they can hold off that total collapse, but only up to a point. And that point is exactly 1.44 times the mass of our own sun. It's called the Chandrasekhar limit. If a star is heavier than this, even this powerful quantum rule isn't strong enough. Gravity wins. The star collapses into a neutron star or even a black hole. This one number is a stunning testament to the staggering power of a single quantum principle.
Okay, so from the insane cosmic scale of stars, let's bring it right back down to Earth. Because this very same rule isn't just holding up stars, it's powering the phone in your hand and the computer you're looking at right now.
So how do we actually harness it? Well, it's all about semiconductors. The entire magic of silicon chips comes down to controlling something called the Fermi level. Just think of it as the energy cutoff point for electrons in a material. By adding specific impurities, a process we call doping, we can actually move this Fermi level around. If you dope it one way, you get an N-type semiconductor, with extra electrons just itching to conduct electricity. Dope it another way, you get a P-type, with what we call holes, which act like positive charges. And this is where it all comes together. When you take an N-type material and you stick it right next to a P-type material, you create what's called a PN junction. This simple little interface is the fundamental building block of all modern electronics. It is the essential component inside every diode and every single transistor, and there are literally billions of them in the device you're watching this on right now. Just look at this timeline for a second. It's absolutely remarkable. In 1925, a purely theoretical idea pops up, the exclusion principle. Just a year later, Enrico Fermi and Paul Dirac formalized the math behind it, and then just a little over 2 decades after that, in 1947, engineers at Bell Labs used that exact understanding to build the very first transistor. That is a direct, unbroken line from a pure quantum insight to a technology that completely remade human civilization. So, we've seen how understanding this rule allowed us to build the modern world, but we're not even close to done. Now, scientists and engineers are moving beyond just using the rule to actively hacking it for the next generation of technology. Yeah, this is the really bleeding-edge stuff. We're moving past just pushing big currents of electrons around to actually manipulating individual fermions one by one. We're creating things called Fermi qubits for more stable quantum computers. We're developing spintronics, which uses an electron's spin, not just its charge, to carry information for way faster and more efficient devices. We're even building artificial atoms called quantum dots and exploring exotic topological materials where the rules of fermions can literally form a physical shield to protect fragile quantum information. We are learning to speak the fundamental language of matter itself. Which leaves us with this final, tantalizing question. We use this one rule to explain why matter exists and to build the entire digital age, and now we're using it to design the quantum future. So what's next? What other realities, what other unimaginable technologies can we build by truly mastering the fundamental rules of fermions? This entire exploration, from that basic puzzle all the way to the future of computing, was all made possible by distilling the brilliant concepts laid out in the comprehensive work of Jörg Uwe Schneepatt.
To explore this topic and so many others in much greater depth, you should definitely visit schneepad.de. Thanks for joining us on this deep dive. See you next time.
Schneepatt.de is a private project by Jörg Uwe Schneepatt dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.